Welcome, our bonus seminar. Our speaker today is Zdeněk Dvořák, who will be speaking about chromatic number of triangle-free graphs. Joint work with Ken-ichi Kawarabayashi from his recent trip to Japan.
Okay, thank you. Okay, so as probably one of the first things that you learn when learning about coloring of graphs is that just forbidding triangles will not help you. That you can get graphs which have no triangles but have arbitrarily large chromatic number. But on the other hand, in many situations you can get better bound for the chromatic number of graphs in some class if you additionally forbid triangles. So let me give some examples. So one famous one is the case of planar graphs, which in general can have chromatic number at most 4. And of course there are planar graphs that require 4 colors. But if they are triangle free, then by the famous theorem of Grach, you only need 3 colors. Or more generally, if you consider graphs on surfaces, so if you consider graph on surface G, then by Ewood's formula, get that the chromatic number is something like at most this. So roughly square root of G.
Is that a conjecture?
No, that is a formula.
But G equals 1 is, or G equals 0 is the planar case.
Yes, well, G equals 0 is true by 4 colors theorem. So just a coincidence. Like for other greater G, this follows by fairly simple argument. And for but if you in the same situation forbid triangles, then Gimbel and Thomassen show that you can actually improve this to something which is on the order of third root of G divided by logarithms of G, and basically this is a correct order of magnitude. There are triangle-free graphs on surfaces that have large genus. There's a chromatic number of this magnitude. Or even if we consider graphs that are not embedded anywhere, so let's say we consider a graph with n vertices. Then on one hand you can have a clique on n vertices which has chromatic number n, but if you forbid triangles, it was shown by Aitai, Komolosh and Semerari that the chromatic number is at most some constant times square root of n over log n. So you get a much better order of magnitude. Or if you take graphs with n edges, then in general it's again easy to see that the worst case is the clique, which has chromatic number roughly square root of twice the number of its edges. But if you forbid triangles, Gimbel and Thomassen prove that again you can improve this order of magnitude to something better. I think third root again. Or if you take a graph with maximum degree delta, then again the worst case is a clique which has chromatic number delta plus 1. And if you forbid triangles, Johansson proved that you can improve this to roughly by roughly logarithmic factor. And presumably on and on, like there are many results of this form. Of course, it's not the case that always when you can prove some bound on chromatic number, you can improve it if you forbid triangles. And an interesting example where this doesn't happen is for d-degenerate graphs. Does everyone know what d-degenerate graph is? Okay, so a graph is d-degenerate if its subgraph has a vertex of maximum degree at most d. So the graph itself has a vertex of degree at most d, and when you remove this vertex, there will appear another vertex of degree at most d, and if you remove this one, you will get another, and so on. And so this gives you an obvious greedy algorithm how to color this graph. You keep removing vertices of degree d, and then you go in the reverse direction, so adding vertices of degree d, and whenever you add this vertex of degree at most d, you give it an arbitrary color which is different from the colors of its neighbors. So to do that, you only need d plus 1 colors.
Shouldn't that parameter change every time you delete?
But it can go down, but it's still the graph is still d-degenerate. Like it's still each subgraph has vertex of degree at most d, even if you remove vertices. So we get that each d-degenerate graph is d plus 1 colorable, and this is again tight because if you take a clique with d plus 1 vertices, all its vertices have degree exactly d, so clearly it is d-degenerate and you need d plus 1 colors. And somewhat surprisingly, even if you forbid triangles, you still need precisely d plus 1 colors. Cannot do better than d plus 1 colors, which is something that was observed by Alon, Krivelevich, and Sudakov, but actually it's based on much older construction of triangle-free graphs with large chromatic number by Zykov from the 50s. It's actually a very nice construction, very simple one. It's not taught that much, but I think it's quite interesting. So, okay, so what do we want? We want to construct some graph GD, which is triangle-free, d-degenerate, and its chromatic number is exactly d plus 1, so we just need to show that it's not d-colorable. So G1 is easy. We can take just an edge, so it's clearly one degenerate and no triangles. We need 2 colors. And now let's construct the other graphs inductively. So suppose we already have the graph GD minus 1. And so how do we get the graph GD? Well, we take d copies of the graph GD minus 1. And now for each each vertex here and each vertex here and so on, for each choice of a vertex from each copy, we add a common neighbor to these vertices. For this choice, we add one vertex, and let's say we choose the same vertices here and another vertex here, we add another vertex for this choice, and so on. So altogether, I will add here something like, well, if this has k vertices, I will add k to the d vertices here. Now, this graph is clearly d-degenerate because we have added this huge number of vertices of degree d, and if we remove them, then the rest of the graph consists of these isolated copies of gd-1, which is actually d-1 degenerate.
So I do have a question. So when you introduce d-degenerate, you say every subgraph has a vertex of degree at most d.
Yeah.
Which, as a consequence, means that you can order the vertices and delete them.
Yeah.
What about the other way around? Are these equivalent
Yes.
definitions or no?
Yes, they are.
So.
Because you just think about the subgraph ordered linearly, and you add in the extra vertices that are in the middle.
Okay. Yeah.
Okay, so yeah, so this is d-degenerate. It is triangle free because we don't have any triangles here, and we are now adding vertices whose neighborhood is an independent set. And it's easy to see that we cannot color it using d-colors. So by induction, none of these graphs, gd-1, can be colored using just d-1 colors. So we need on each of these copies use at least d colors. So the only way how we could possibly color this using d colors is if we use all of them on each of these copies. So we will need to use colors 1 up to d here, and 1 up to d here, and 1 up to d here. But then I can pick here a vertex which has color 1, and pick here a vertex which has color 2, and pick here a vertex which has color d, and I have this common neighbor which I cannot color without using an extra color. So I cannot possibly color this graph using just colors. Okay, so forbidding triangles doesn't always help. So somehow the question that we consider with Ken-ichi doesn't directly follow that we would want to prove more results of this form. We had a different motivation, which I may go into at the end of my talk if I have time. But anyway, I think it's interesting to ask whether you can find something like in between these two worlds. So whether you can find some natural class of d-degenerate graphs for which forbidding triangles would help you. And the class of graphs that we decided to consider was the graphs with bounded tree width. Let's consider graphs. Tree width at most. Does everyone know what tree width is?
I always forget every time.
Okay. So let me quickly describe how you can construct a graph with tree width at most t. So you start from an arbitrary graph on t plus 1 vertices, or at most t plus 1 vertices. And then inside this graph, you can pick any subset, and add another subgraph which has again at most t+1 vertices, such that well, with an arbitrary intersection, and then you repeat this construction again. So maybe you will add another part of the graph here with at most +1 vertices, and so on. And you can add such a piece to your graph under the condition that the intersection is contained in one of these blobs that I was adding here before. So I can, for example, add another piece whose intersection would be this thing. So on this I can attach new stuff, but I cannot attach something which would intersect this with a part here and a part here, because these two things are not fully contained in one of these pieces that I added before. And so you see that this will force me to grow the graph somehow in a tree-like fashion. I have started here from this root graph, and then I let's say attach these things that are like the children of this root node in the tree, and then I may give them further children, and so on. So you can define this formally. So a tree decomposition of a graph is where t beta, where t is a tree, and beta is a function that to each vertex of the tree assigns a set of vertices of G. Which must satisfy some condition. So each vertex and each edge must be contained in the image of one vertex of the tree. So everything that we added must be in one of these blobs. And finally, we need something to express this condition of that the things will look tree-like, that the intersections are kind of nested in this nice way. And one way how to do it is to say that if I have a look at the blobs that contain any single vertex of my graph G, these blobs must induce connected subtree of this T. So for every vertex of G, if I have a look at the subforest of this tree induced by those vertices of the tree, such that B is in the blob of X, then this is actually connected subtree. Anyway, so this is kind of a formal definition, which will not really be that important for us. what you should have in mind is some picture like this, that it's a graph that can be somehow grown in a tree-like fashion. And now the width of the decomposition is the maximum size of the blobs. -1 because I want to mess with you. Well, it's historically defined this way. And the tree width of a graph is the minimum of the width of all its possible tree decompositions. So, if I have a graph with tree width at most t, I can create it in this way using blobs of size at most t+1. So this is a little bit technical, but it's an important motion, especially in algorithmic graph theory, because there are interesting algorithmic theorems that tell you that many problems that are difficult in general, let's say determining the chromatic number of a graph, become polynomial time solvable if you consider them on graphs which have small trees. And there is then a lot of applications in the algorithmic setting of the form that, let's say, maybe you can take your graph which doesn't have a small tree width, but you can do some perturbations on it and make it to have small tree width, and then use that to get polynomial time algorithm for the original graph or things like that. Anyway, for us, it's what will be the interesting for us is that actually having tree width at most t implies that the graph is d-degenerate. And that is easy to see because you just have a look at the last blob that you added, and so you added this blob of size at most t+1, and in that you added some vertex which can only have neighbors within this blob, and so this vertex must have degree at most t, and it's easy to see that this also holds hereditarily, that in any subgraph. Any subgraph also has tree width at most t, and therefore it must contain vertex of degree most. So the graph is d-degenerate. If you don't forbid triangles, you still don't get any better bound than for the degenerate graphs. You get that the chromatic number is at most t+1, again because of a clique. If you take a clique on t+1 vertices, you can just put it to a graph in the first step. So this clique has tree width at most t, but you need t+1 colors. And so it is interesting to ask whether forbidding triangles will help you, or whether it will not. So whether it will be more like still this general d-degenerate case, or whether it will be like these cases that I did. How can you color a graph with bounded? Well, there is kind of an obvious way how to do it. You have this tree structure, so you do it somehow following this tree. So you can either try to start somehow from leaves up, which will not work very well for us, or you can start from the root. So the way you could color this graph is you fix some coloring of the vertices in this root node, then you fix the colorings or colors of the vertices in the neighbors of the root, and so forth. And now, how should you decide? So let's say we already somehow decided how we will color the root of the tree. So what you should take into account when you are coloring these vertices? Well, obviously you don't care about these other parts of the graph. Whatever colors you give here will not in any way affect the coloring here, because you will not ever get any edges between these parts and these parts. These two parts of your graph can only communicate via the vertices of the. So when deciding how to color this thing, it only makes sense to take into account this graph here. But it actually turns out that it doesn't even make sense to consider what the things that attach here, because I have freedom to essentially attach to here in any plausible way. So let's say if I have this node, so there are only finitely many different ways how I could attach a child to this node, still keeping it with bounded tree width and triangle free, let's say. So I can choose how many vertices I will add in the next node. I can choose their neighborhood in such a way that I don't create triangles, and I can choose what their block that contains them will look like. I have frankly many ways how to do it, and I can just put all of them here if I want to make the things as hard to color as possible. So I will have this chart for every possibility how it would look like, and then they will have all the possible choice for all the possibilities and so on. So I cannot really capitalize on saying, okay, here I don't have charts which look like this, because I can have all the possible ways. So really the only thing that I can reasonably take into account when coloring these vertices is what colors I already used on the root. And it's kind of convenient to look at this in some kind of online coloring setting. So you may look like it that let's say I will be coloring things along some path in this tree, and I can look at it that at this point I don't know how the rest of the graph will look like, because it can look all the possible ways. So I will decide on this coloring, and then my enemy will reveal me this part of the graph that I should color next. So instead of trying to color this graph with bounded tree width, I can look at it as some kind of online coloring problem where I have an enemy who creates the graph on the fly and tries to force me to use many different colors. So the enemy somehow creates this root node and forces me to tell him how the root node is colored, and then based on what coloring I chose here, he tells, haha, here is the next node, and I have to color the vertices of this node, and so on. But now I can just assume that he proceeds in this path-like fashion, always only creating intersections with the last leg. And based on this little bit hand-wavy idea that I just told you, it's easy to see that these coloring problems are equivalent. So if you can color each such graph using K colors, then you will get a strategy for this online game, such that your enemy will never force you to use more than K colors. And if you have a strategy that beats every opponent using just K colors, then you will be able to color the graphs with bounded tree width as well. Okay, so let me use this to show you let's say the lower bound for this problem. So let me show you that there exists a graph GT which has 3 with at most d, it's triangle free, and it needs at least d plus 3 over 2 colors. So I will. So by so in this online coloring setting, I am now playing the role of the enemy, the one that produces the graph, and I'm trying to show that no matter how cleverly you will try to color the graph, I will force you to use at least this many colors. So yeah. Okay, so maybe this will be really the easiest way how to show how it works. Let's play this game. So I will start the graph using one vertex. What color you want me to use for this vertex?
1.
Excellent.
We
So-
get to choose the color, or?
Yes.
So
He gets to choose the graph.
Oh, he's making the graph.
I make it. So okay. So I will then, as the next step, I will take a blob of size 2, and I will add one more vertex to it without any edges. What color do you want to use?
1.
1.
Excellent.
Oh, they are winning.
So I will add.
I think he's setting us up for a trap.
I will add another vertex, and now I will join it with this vertex here. So I can do the decision by you. For you, we will use color 2.
You wanted to use color 1.
We've lost.
Okay, so I've now forced you to use 2 colors, but that's still not too many. Okay, so let me now add another vertex. Now I will just, in the next blob, I will drop this first vertex. So from now on, my blob only contains these last 3 vertices. And I'm not making it adjacent to anything. So what color would you prefer for this vertex?
You're going to trick us, but 1.
No, no, 2,
No
2,
matter whatever
2.
he draws, we can always.
Who wants 1?
Put 3, then we're safe.
Okay, so we need to vote. Who votes for 1? Who votes for 2? Who votes for 3?
I'll vote for 3 just because I don't know what you're gonna put.
Okay, so we have 2 here. So let me continue. I will add a vertex which will neighbor just here. Still fall over in this block. So what color do you want to use here?
1 was so fun, so I was thinking.
Okay, let's do 1. So I will now need a blob which has size 5 to make forward, to proceed forward. So I will need all these into the blob, and I will make it adjacent to these 2 here and 1 here. So this forces you to use colors. And so okay. So what is my overall strategy? I'm trying to force you to use many different colors on an independent set that is contained in the last block. So at this point, I forced you to use 3 different colors on this independent set, which is contained in the last block. And so once I did that, I will forget everything that I did so far. So in the next block, I will just contain these 3 vertices and whatever I am adding to them. And always, as the first step, I will add an isolated vertex, for which you presumably will use one of the colors 1, 2, and 3. Let's say 1, as the next vertex, I will then add a vertex adjacent to whatever color you chose here. So now this forces you to use, well, colors 2, 3, or 4. So let's say use 2, and then I will add a vertex like this, and let's say you try to escape and give me 4, and well, then I have an independent set, and then I colors 1 up to 4. So somehow, as the worst case, if I already get colors 1 to up to k, to force you to use color k plus 1, I may need to add the isolated vertex and the neighbor of this vertex and neighbor of these two, and so on. And finally, a vertex which is adjacent to all the vertices in my preceding independent set. For that, you will need k plus 1. So to force you to use colors 1 up to k plus 1 on an independent set, I will need blobs of size 2k plus 1, which explains why the number of colors that I will get is roughly half of the 3s. And the round 8 and so on is just, this should be rounded up actually. It's just a matter of computing how things are. Okay, so I can, the enemy can force us to use like half the colors. On the other hand, this number of colors is actually sufficient. And the algorithm to do this is what kind of not to involve. So let's say I have already somehow colored this initial part of my graph, and I'm coloring the next blob. Well, I can as well assume that in the next blob I have just single vertex attaching to something here, because I can add the vertices of the blob 1 by 1. So obviously, when I'm coloring this vertex, I must avoid the colors on my neighbors. So I would like to have chosen the coloring up to here in such a way that on this neighborhood I haven't used all possible colors. So I still have at least one color available. And well, I don't know how the future will look like, so at this point, so I don't know where this vertex will attach. But because the graph is triangle free, I know that this neighborhood will be an independent set. So my strategy is to color in such a way that on no independent set am I using all the possible colors. So that restricts me a little bit when I'm choosing not on any independent set which is contained in the last bag. So that restricts me a bit when choosing the color of this vertex. So at this point I still cannot use the colors used on my neighbors. But I also must avoid choosing a color here which would lead me to violating this condition. So if I have an independent set here on which I use colors, all colors, but some color C, then I cannot use C on this vertex because I would be getting an independent set. No, should have drawn it here in this intersection. I cannot put C here because now I would be having an independent set on which all colors are used. And now you need to do some argument and actually show that even if you are forbidding the colors from being used here in these two ways, being the neighbors or being the last color missing on an independent set, it still will not be able to forbid you all the colors if the number of colors that you are using is large. And the argument is not very hard, but not too interesting, so I will not go into it. Rather, I would like to end my talk with a few problems. So first of all, my talk was about triangle-free graphs, but you can similarly ask what happens if you forbid larger cliques. So let's say what happens if you take a graph which has 3 widths at most t and largest clique has size k, and you ask what you can say about the chromatic approach. And using similar idea like this one here, you can show that this upper bound cannot be anything better than something on the order of this. So you can show that there exists graph with these properties, which let's say for if they are K4 free, still needs something like 3/4 of the colors. But we don't really know how to prove any upper bound there, so we don't. Second thing, we did this argument using this online coloring of graphs, for which we got just the 3D composition, which looks like a path. So a graph with bounded pathways. And so it's kind of interesting to ask. So now we know this exact bound for this online coloring of graphs with bounded pathways. But then we can go back and ask what is the normal chromatic number. So let's say if you have a graph with pathways bounded by t, and let's say triangle free, what is the upper bound on its chromatic number? So obviously the same algorithm still works here, so we get at most this many colors. On the other hand, the lower bound proof no longer works, because now we have just single feature that can happen in this graph. We don't have this online branching for all possibilities. So I suspect that here this bound should be substantially better. That it should be probably on the order of t over log t, not on linear order. And finally, this is a little bit. So we have seen that for these d-degenerate graphs, the chromatic number forbidding triangles doesn't help you with the chromatic number. But what is not known is whether it helps you with the fractional chromatic number. And if you don't know what fractional chromatic number is, just phase out this part of the talk, because I'm not going to explain it in the remaining -5 minutes or whatever time I have. So the question would be, if the graph is d-degenerate, triangle free, what is the bound on upper bound on its fractional chromatic number? And I don't know any good upper bound. I don't know any great lower bounds either. If you have a look at this construction, this tells you that the fractional chromatic number goes to infinity. It is known that the fractional chromatic number of this graph GD is precisely equal to the fractional chromatic number of GD minus 1 plus 1 over fractional chromatic number of GD minus 1. So this gives you some sequence of graphs whose fractional chromatic number grows to infinity, although very slowly. But I don't think this is the correct answer. I think that there should be some more involved construction or something which will show better bound. I don't know what the upper bound should be. Thank you for your attention.
Question? If no question, let's thank Zdeněk again.